Good afternoon, I am Mr. Ish. Thank you for joining me. Here in this specific video, we have this title, Solving Differential Equations with Confusing Constants. What does that mean? When you're given a differential equation, normally with the y and the x variable, it's very easy to understand what you're looking at. Anything which is not y, which is not x, anything beyond that, you consider that to be a constant. When you're looking at something like this, how do you understand or relate which of these letters refers to variables and which of these relate to constants? The single best clue that you can think of is just by looking right over here. Derivative with p over derivative with t, change in p over change in time, or change in t. When you're looking at this, you're seeing p's and t's are involved with these derivative factors, so clearly they must be your variables. Anything beyond that must not be a variable and it would be treated as a constant. And that's the single best theme or point that I can give you in this particular video. If you're asked to solve this differential equation, you know you're not seeing x's and y's, but you're seeing everything else. You would start something like this, first of all, by not confusing yourself or getting overwhelmed. You've already determined what the variables are simply by looking at this derivative with respect to p and derivative with respect to t. So you know p and t are variables. You can open this up. You're looking at km. Whatever that means, we don't know what it means. Minus kpt with respect to time. If you were to take this on the other side, look what would happen. You'd have derivative with p or of p over time, change in time, plus kpt is equal to km. Now what do you think you end up seeing right over here? You end up seeing very likely a linear first order differential equation. It's first order because you have dp or dt. There's no squares involved, and it's linear because it looks like something like this, dy over dx plus py is equal to q. It looks exactly like that. The k and the m are your constants. When I'm looking over here, I'm thinking about a linear, therefore I'm thinking about a integration factor, e exponent integral k dt. Don't put an x over there because everything here is with respect to dt. When you're doing this, you're getting e to the power of kt, which will then multiply with everything you see over here. When you do that, you'll have e to the power of kt dp or dt plus, I'm going to put this k first, which is fine, then e to the power of kt pt is equal to, I'm going to put km first because these have been determined to be constants, and this right here will have the variable attached. What's the variable over here? It's t. This has come here from a derivative or implicit differentiation of something. What is that something? Look right over here and look at this and combine them. Derivative with respect to time, d or dt. Don't put an x over here. There's no x's involved. You have e to the power of kt and then pt is equal to that. Km e to the power of kt. We can close this. If you were to do the product rule, implicit differentiation, you'd get this. Think about it. X and Y's, that's what you're looking at, the product rules. This would multiply with the derivative of this, which would be dp or dt, and that's exactly what you see. This would multiply with the derivative of this, which would be k e to the power of kt, which is exactly what you see. So you're on the right track. This will now be integrated right here with respect to dt. You're seeing all of that. That will cancel out. You'll have over here e to the power of kt pt is equal to, now you have to do the integral of this, but the integral of this is not hard. You have a km. You're really looking at km and then the integral of that. You could have pushed this integral sign right over here to right here, right after the two constants, and you'll be looking at that. This is no different than you looking at something which is e to the power of ax. You're doing the integral of that. You'll have e to the ax over a. That's exactly what it is, plus c. So let's utilize that scheme we have and bring it into play. When you're doing that, you have a km e to the power of kt over k. This is my e to the power of ax over a, e to the kt over k plus c. That's exactly what I have. But look what happens when I do this. This k and this k cancels out. They cancel out and you can erase them out. And that's exactly what I'm doing here. I had km e to the power of kt over k. The k's cancel out. So I have this is equal to that. I'm solving for this. This is really like my y variable is equal to all of this divided by that. When I take this on the other side, it divides. It'll cancel out with that. I'll have m plus c over e to the power of kt. But you can write that in a better way if you want. You can do pt or your variable, your y variable, it's not really a y variable, but it's similar to a y variable, is equal to m plus c e to the power of minus kt. And this right here would be the equation or the function for which this differential equation was true. And remember, this differential equation did not have the x and the y's, therefore it was confusing for many students from the start. Many students will look at this and they'll get lost. Again, the single best clue is to look at this derivative factor. The letters you see in there are the variables. I saw a p and a t, they became my variables. Everything else which is not a p and a t became a constant, and that's how I would go. Because we're looking here at a first order differential equation, its level of difficulty is not very hard, and it turned out to be a linear first order differential equation, and this right here is my answer. Pt is equal to, or you can say your p variable with respect to time is equal to m plus c e to the power of minus kt, and your question has been solved. And that's all I wanted to present to you in this video, the main theme being identifying your variables from your constants. Thank you, have a good day.